This question asks about the effect of increasing the alpha parameter, which controls the strength of L1 regularization, in graphical lasso. Increasing alpha means a stronger penalty is applied to the non-zero elements of the precision matrix, inverse of the covariance matrix. This will impact the sparsity and bias of the estimated covariance matrix. The question sets the stage to test understanding of the fundamental concept of the alpha parameter in graphical lasso, a popular technique for estimating sparse covariance matrices. Let's explore the options to answer this exciting question. This option explores the possibility of increased density, more non-zero values, in the estimated covariance matrix as alpha increases. This would counter the regularizing effect of the alpha parameter. We'll need to explore further whether this is true or not. This statement suggests that as alpha increases, the resulting covariance matrix becomes sparser, containing more zeros. This is a key aspect of L1 regularization, implying that increasing alpha will shrink more elements of the precision matrix to zero. This will reduce the number of non-zero elements in the inverse precision matrix, covariance matrix. We need to consider whether this directly relates to the L1 regularization process. Overfitting occurs when a model learns the training data too well and performs poorly on unseen data. This option explores whether increasing alpha might cause overfitting. Does the regularization actually increase the risk of learning the noise in the training data? Let's investigate that. This option proposes that increasing alpha introduces more bias. Bias refers to systematic errors in estimation. Increasing the regularization strength would pull the estimates towards zero, increasing the systematic error. We need to evaluate the relationship between alpha and bias in the estimation procedure. Let's break this down. Alpha is the tuning parameter in our graphical lasso model. It controls the strength of the L1 regularization. Increased alpha directly translates to stronger regularization. Think of regularization as a constraint. The higher the alpha, the more we're forcing the model to shrink its parameters, coefficients within the covariance matrix. This constraint is directly related to the sparsity of the resulting covariance matrix. Sparsity refers to the number of zero values in the estimated covariance matrix. A higher alpha results in a sparser matrix. This is because the strong regularization pushes many of the estimated relationships between variables toward zero, effectively eliminating them from the model. In essence, a higher alpha promotes a simplified representation of the relationship between variables by setting many relationships to zero. L1 regularization, short for L1 penalty, is a type of regularization technique used in machine learning to prevent overfitting. It adds a penalty to the loss function proportional to the absolute values of the model's coefficients. In the context of graphical lasso, a higher alpha means a stronger L1 penalty applied to the precision matrix. This encourages sparsity in the model, meaning more of the coefficients get shrunk towards zero. Think of it like this. Imagine you're trying to fit a curve to some data points. A high alpha discourages the curve from becoming too wiggly, essentially simplifying the model. This is analogous to the idea of keeping things simple and avoiding unnecessary complexity. This prevents the model from memorizing the training data too closely. In the context of covariance matrices and graphical lasso, sparsity refers to the presence of many zero values. A sparse covariance matrix indicates that only certain variables have direct relationships, while others are conditionally independent. Increasing alpha in graphical lasso increases sparsity by shrinking the values towards zero in the precision matrix, resulting in a sparser estimated covariance matrix, its inverse. The more zeros, the sparser the model, which can be preferable in high-dimensional data. The bias-variance trade-off is a fundamental concept in machine learning. Bias refers to how much a model's predictions differ from the true values, systematic error. Variance refers to how much a model's predictions vary across different training sets, random error. Increasing alpha in graphical lasso increases bias by shrinking the estimated covariance matrix towards zero, but decreases variance and reduces the risk of overfitting. It's a delicate balance. A high bias might result in the model being inaccurate but consistently inaccurate, less variable. High variance means the model is more accurate on average, but more likely to change depending on the training data, more variable. The best model generally strikes a balance between the two. In our quiz, increasing alpha means we're accepting more bias to decrease variance. Hey Vamsi, let's break down how L1 regularization affects the graphical lasso. Remember, a higher alpha means a stronger penalty on those pesky non-zero elements in the precision matrix. Think of it like this: the higher the alpha, the more aggressively it pushes the less important connections towards zero, making the precision matrix, and consequently, the covariance matrix, much sparser. Okay, now let's talk about the bias-variance trade-off. When you crank up alpha, you're essentially increasing the bias. Your estimates are getting pulled closer to zero. But hey, that comes with a benefit. You're decreasing the variance, which means you're reducing overfitting and avoiding those overly complex models. Alpha is the control knob for the strength of L1 regularization in the graphical lasso. It directly influences how many connections, edges, in our graphical model are deemed unimportant and are therefore zeroed out. So, when alpha is increased, the estimated parameters are shrunk towards zero, meaning a larger bias. We're accepting a simpler model, higher bias, in return for lower variance, reduced overfitting. It's a careful balancing act. Imagine it like tightening a net. It gets more accurate in its general shape, but smaller details may be lost. See, this is directly related to the L1 regularization. As alpha increases, the penalty on non-zero elements gets stronger. This makes more and more of the elements in the precision matrix become zero. The resulting precision matrix, and thus the covariance matrix, becomes sparser. This is the core question, Vamsi. We're exploring how increasing alpha in the scikit-learn graphical lasso impacts the results. The key here is to understand that the alpha parameter directly controls the sparsity of the resulting covariance matrix. This sets the stage. We're using the graphical lasso algorithm, a powerful tool for estimating a sparse covariance matrix, and alpha is a hyperparameter, meaning it controls how the algorithm works. It is a tuning parameter we can adjust. Higher alpha equals greater than stronger regularization equals greater than sparser graph. This line summarizes the core relationship between the alpha parameter in graphical lasso and the resulting graph sparsity. Increasing alpha strengthens the L1 regularization, which forces more coefficients in the precision matrix towards zero. This results in a sparser graph, where fewer connections between variables exist. Imagine a network. A higher alpha cuts more connections, making it more sparse. L1 regularization. This refers to a type of regularization technique used in graphical lasso. L1 regularization adds a penalty proportional to the absolute value of the coefficients in the model. This penalty encourages some coefficients to become exactly zero, thus leading to sparsity in the model. Think of it like a tax on complexity. The model is incentivized to be simple, sparse, to minimize the tax. Alpha, regularization strength. This clarifies that the alpha parameter controls the strength of the regularization. A larger alpha value implies a stronger penalty, promoting increased sparsity. It's like a knob you can turn to control how much regularization you want to apply. Graphical lasso. This is a specific algorithm in scikit-learn, a Python machine learning library, used for estimating a sparse covariance matrix. It uses L1 regularization to achieve sparsity, which is important when dealing with high-dimensional data or when a simpler model is desired. It effectively helps us to discover relationships between variables without overcomplicating our model. This represents the alpha hyperparameter in the graphical lasso algorithm. It's a tuning parameter that controls the strength of the L1 regularization. Think of it as a dial. Turning it up, increasing alpha, increases the regularization strength, while turning it down decreases it. This is a type of regularization technique used to prevent overfitting in statistical models. In the context of graphical lasso, it adds a penalty to the model's objective function based on the absolute values of the model parameters, coefficients. Higher alpha values mean a stronger penalty, making the solution simpler and less prone to overfitting. L1 regularization, controlled by alpha, enforces sparsity in the model. This means that some of the model's parameters will be forced to exactly zero. This is desirable in cases such as the one presented, where we want to estimate a sparse covariance matrix, a matrix with many zeros. This makes the model simpler, more interpretable, and less prone to overfitting. A higher alpha will lead to more zeros and a sparser model. This is a fundamental concept in machine learning. As we increase the alpha value, we increase the bias of our model, meaning it makes stronger assumptions about the data. It forces the model to fit the data more poorly. However, it simultaneously reduces the variance, meaning that it becomes less sensitive to fluctuations in the training data. The trick is to find the sweet spot, the right amount of regularization, alpha, where the increased bias is worth the decrease in variance and the overall model error is minimized. With the right value of alpha, we aim to reduce overfitting, which is when our model performs well on training data but generalizes badly to the unseen data.